Hi folks, this is Dr. Minders again. In this video we're going to talk about Laplace transforms. This should be review from your differential equations class, but certainly in differential equations you talk about Laplace transforms as one method of solution of a differential equation, and in mechatronics we're looking at Laplace transforms as pretty much the only method that we want to use, and I will show you why. So first of all, let's remember our general input-output ODE. So here it is at the top. We've got n terms on the left, and we've got m terms on the right. So we have n derivatives of our output, which in this case we've called y, and we've got m derivatives of our input, which in this case we've called x. Now sometimes we might change those variables up. Remember, x and y are not the only ones that we like. We might call the input u, we might call it f for force, we could call it lots of things. But if we have an ODE like this that describes the system, then we want to talk about the time response. And we haven't talked in class about time response, and we definitely will next. But the time response is essentially how the system output, y in this case, changes as a function of the input x. And we know that there's a differential equation that describes it, and so there's going to be essentially a memory effect from this differential equation. And so we want to look at how the system evolves. And so, for instance, if you think about a tuning fork, you whack it, it rings for a while, and the ringing dies away. We want to be able to model that ringing, but also the dying away effect. And that's the sort of thing that's encapsulated in a differential equation. So, in our time response, the solution of the differential equation, in your differential equations class, you probably learned that there's a particular and a homogeneous solutions, denoted in this case as y sub p and y sub h. And so we know that the particular solution is the steady state portion of the solution, what remains after the transient portion goes away. And the homogeneous solution, which is that transient portion. So the homogeneous is going to do something like the tuning fork ringing and then dying away, and then the steady state is what's left. So in the tuning fork example, if you whack it, it dies away to nothing, and so the steady state would be nothing. But if you push you push a block and it oscillates a little, it's going to end up at that steady location that it was pushed to. So in our differential equations class, we learn how to solve these. And so we always have to choose some particular solution and solve for that one, and choose some homogeneous solution and solve for that one. And then we add them up and we find a total solution, which we call y of t. And then finally, we'll use our initial conditions, what happened at time 0, to figure out what the unknown coefficients were. And remember that we only are dealing with things that vary in time, not in a second variable. So you think about your heat equations, your beam equations, they often were in terms of a position where you'd fix one end of a beam or fix the other end of the beam. We're not worried about those. We're only worried about things that are evolving with respect to time. So this is the way you've done it before, and you probably have lots of practice with this. So for instance, we might have a thermocouple. A thermocouple is a measurement of temperature, and it's a joining of two different materials, and it produces a very small voltage across the join based on the temperature. So that particular system experiences what we call a first order response with respect to temperature. So if we put in a temperature x in this case, we'll get out a very small voltage response y. And the speed of that response is denoted by the time constant, and the amplitude of that response is the static sensitivity. And don't worry, because we're going to go over all that in a later class, but for now, it's a differential equation. It's a differential equation that has one derivative, which makes it easy for this. And we want to talk about a step response, which is to say that it's going to be a sudden change. So we're going to take our thermocouple, and it's got this model, and we're going to leave it at room temperature until it's nice and steady, and then we're going to suddenly change the temperature. Say we're going to drop it in hot water. And so that's a step. The step is a sudden change, and it's a sudden change that stays. It's not like you whacked it like an impulse sort of thing. You have dunked it in the water and left it in the water. And so the temperature that the thermocouple is seeing has jumped from 25 degrees to 80 degrees C, and so the temperature induces a voltage change, and the voltage change is going to change, but it's going to change as a function of our first order ODE. So how do we do that? Well, we put in our known things first, which are our k and our tau values, and then we find our particular solution. This is our first step. So we know that the input is a constant, well, step input, 80 degrees C. And so we know that our particular solution, our steady state value, must be a constant to match our input type. Remember, your steady state solution should match the same input type. If we put in a sinusoid, our particular solution should be a sinusoid. If we put in a step, it should be a step. So in this case, we will just choose it to be some V sub SS for steady state. So if we substitute in, we're going to take our y's and replace them with our VSS. And so we get 0.1 times the time derivative of VSS plus VSS is 0.005 times x. Great, that's our particular solution. What can we do with this? Well, we know that because VSS is a constant, that the time derivative must be 0. So let's get rid of that. And so the only thing left is the particular solution must be 0.005 times x, and we know that the value of x is 80 degrees C. So VSS must be 0.4 volts. Done. We have a particular solution. So let's move on to the homogeneous solution. So if we let the input be 0, then what's left is tau times dyh dt plus yh equals 0. So now we need to solve this for y sub h. Well, I happen to know, and this is the tricky part, is that if you don't happen to know what it is, what do you do? I don't know. That's DiffyQ class time. I happen to know that this type of system is solved by y of h being ae to the lambda t. Now, a is unknown, lambda is unknown, t is our time. And so if I substitute this in, what I'm going to get is the derivative of ae to lambda t must be just lambda ae to the lambda t. So let's drop that in. So we get tau lambda times ae to the lambda t plus ae lambda t equals 0. So if I pull out the ae lambda t, and that's one thing, multiplied by tau lambda plus 1, I know that e to the something is not going to cross 0, and so I'm going to know that ae to the lambda t can't possibly ever be 0, so the tau lambda plus 1 must be the thing that goes to 0. So there we go, we'll pull that out, and so lambda must be negative 1 over tau, and I know my value of tau, so lambda must be negative 10. So there we go. We know what the homogeneous solution is. It must be ae to the negative 10t, but I still don't know a, and I do know lambda, so I've still got one unknown that I need to solve for. And this, just as an aside, this tau lambda plus 1, that's what we're later going to call the characteristic equation of a first order ODE. And you may have heard that term before, characteristic equation. We'll cover that later, but just notice this, that you've seen it now, and so when I mention it in class, you're going to say, aha, I remember that. That's the characteristic equation of a first order ODE. So let's form our particular, we already found the particular, forget that. Let's form the total solution. So there's the particular plus the homogeneous. We'll add them together and we get y of t. And we know what those values are now. It's VSS and ae to lambda t. And so we need to match our initial conditions. And if we match our initial conditions, we should be able to solve for that a, because we know VSS and we know lambda. The only thing we don't know is a. So we need to have one equation, and we have our one unknown is a. So let's use one initial condition. So that'll be time equals 0 seconds. And so at time equals 0 seconds, y of 0 is k times t of 0, which happens to be 0.005 times 25 degrees C. I should have put in some units there, but you know the units here, so it's going to be 0.125 volts. So there's our equation. We will match it up and solve for t equals 0. And so it's going to be 0.4 plus ae to the negative lambda, which is 10 times 0. So 0.4 plus a is 0.125, so a must be negative 0.275. So there is our final solution for the ODE. We know that y of t for a step input, and this is particular to the type of input that we used, for a step input, y of t is 0.4 minus 0.275 e to the negative 10t volts. There we go. That is our solution to the ODE. So what's it look like? It's going to start at 0.125, which is the voltage that matches up with our initial room temperature, 25 degrees C. And then That's at time 0, we dunk it in the hot water, and so after a while it's going to reach 0.4 volts. That is our final value. But how does it get there? Well, it jumps up a lot initially, and then it slowly approaches it. And so that shape that you see, that's a very characteristic shape of a first-order ODE. It's a exponential sort of shape. So there we go. There's our time response of a first-order ODE, and I hope you can see that this is sort of a tedious solution. It's not fun to do. Let's look at it again in a slightly different perspective with some nice graphs. So we've got our particular solution, which is a step. It starts at 0 and then it jumps up to whatever the final value is going to be. We've got our homogeneous solution, which is always in general going to be k times T naught minus T, so initial value of the temperature minus final value of the temperature, e to the negative T over tau, which is always going to look something like this. It's going to start flat, it's going to spike down, and then it's going to take this exponential rise back to 0. And if we add those two together, you can see that we're going to have our step plus our spike down and then back up, and when you add them together you get the purple, which is that characteristic shape of a first order ODE. So graphically that's what we just did. We found these terms, and we know for a first order system it's always going to look like this for a step response. So here's what we did. If I can get my pen to work. Awesome. We took a differential equation with our initial conditions and we went straight across to y of t. And it took 4 different steps. We found particular solution, homogeneous solution, we added them up, we found our initial conditions. It's tedious. It is very tedious, and it requires knowledge of what the particular solution is going to look like, what the homogeneous solution is going to look like. It's not fun. So let me label this here. Tedious. I don't like that way. What I like instead is this other route that we're going to take, and this is how we're going to do things in 3214 in our mechatronics class, because it's going to result in an easier solution. We're going to jump from our ODE to Laplace transforms, go away menu, to an algebraic equation, and that algebraic equation is going to be in what we call the S domain. And S is this special domain caused by our Laplace transforms. But it's algebra, so we can very easily redo the algebra so that we get y of s. Notice there's a capital Y of s. We're going to use caps to denote Laplace transform. It'll easily result in a y of s just through algebra, adding, subtracting, multiplying, dividing. Nothing tedious, nothing that you absolutely have to know the form of the solution like you do the other way. And then we'll just take that and we'll go back through Laplace to the time domain. And so while it takes more steps, this route is easy. And you'll see that with some examples, but guaranteed this is the easier route, and it's going to enable us to look at the system in the Laplace domain, which will tell you a lot about the behavior without having to go back to the time domain every time. We can do a lot of nice stuff, and we can put it in MATLAB and Simulink in Laplace. So sometimes we'll go all the way back to time domain, sometimes we'll just go to Laplace and find the solution, but it is an easy solution. So if we want to do that, we first have to be able to do complex numbers, and so we're going to do a quick review of complex numbers. It's stuff you've seen before. Remember that a complex number is something that's got both real and imaginary components. So for instance, z here on our real imaginary plane, and we're going to deal a lot with the real imaginary plane. Z has a real component and an imaginary component. And the imaginary component you may have seen before denoted as I. You're going to see it denoted by J every time I'm writing notes. A lowercase j for me is going to be the imaginary number. So remember, that's going to be square root -1. And if you use MATLAB, I and j are both going to be the imaginary number. And so when you're using MATLAB and I tell you not to use j as a variable, that's why. Because it's in MATLAB, it's the imaginary number. So think about how we represent things. You're very familiar with Cartesian coordinates. Cartesian coordinates are your standard form. We're going to move across on the real component x, up on the imaginary line y, and that gets us to z, and so we can say that z is equal to x plus j times y. That's your Cartesian form. And so remember, the real component will be x, and the imaginary component will be y. Not j times y, just y. And this gets back to our vector notation. Real component x, imaginary component y. So this is Cartesian form. This is one very nice way to do things, and you'll see that we're going to use it sometimes. But you could also represent them in polar coordinates. And in polar coordinates, think about it as a vector from the origin to z, and that vector has length of a, an angle relative to the real axis of theta. And so we can call that phasor notation. And so in phasor notation, z is going to be equal to ae to the j phi. And if you look at that, ae to the j phi, you're going to think to yourself, that looks a little bit like the solution we just saw, and it's going to be important later. Remember that Euler tells us that e to the j phi must be cosine of phi plus j sine phi. So you can see right away that there's going to be a connection between phasor notation and Cartesian form through Euler's rule. So in this case, we will call a the magnitude, the length, of the vector from the origin to z. And we'll talk about theta, the angle there, being what we call the phase. You can also call it an angle, but phase is the notation, and you're going to see it a lot lately in what we call a Bode plot. So this all is going to it's all going to show up a bunch of times. You're going to get a lot of review, but just remember, we can use Cartesian or we can use polar. They are equivalent forms. They are the equivalent forms of the same thing. And they both represent complex numbers, and they both have their place. So certainly they are equivalent. If we have it in Cartesian, well, we can find that x and y are clearly equal to a cos phi and a sine phi. And if we want to go the other way, we could say that a is going to be the square root of x squared plus y squared, and phi is going to be a tan 2 y of x. And what is a tan 2? It's like tan inverse, but it's got some special rules. It's a MATLAB command. atan2 is a MATLAB command. It shows up in other languages too. But what it means is inverse tan with potentially an extra pi or without an extra pi, so that we get in the right quadrant. If you think back to your arctan, arctan always puts things into the first or fourth quadrant, but we know that it's not necessarily always in the first or fourth quadrant, so sometimes we have to rotate ourselves around to get into the correct quadrant. So atan2 automatically puts you into the correct quadrant, as an aside. So we've got complex numbers, and once we've got our complex numbers, we can start talking about Laplace transforms. Laplace transforms, there's a nice formula here. We can say that the Laplace transform, capital F of s, is the Laplace transform of little f of t. So little f is going to be time domain, cap f is going to be s domain. It's just kind of my convention. And the one-sided Laplace transform is going to be the integral 0 to infinity, little f of t, e to the negative st dt. S is a complex variable, see that's where we need the complex numbers, and S is going to be defined by sigma plus j omega. F of t is a complex, or as a continuous function, sorry. And so it's going to convert this into a function of complex variable S. So we're going to go from variable of time to variable that is complex. And it does have an inverse, so we can go back and forth, and there you can see the inverse. But realistically, what we're going to do is we're going to figure out some standard forms, and we're going to use tables. We're not going to apply this rule. This rule is tedious. We've got a standard table of transforms. It's in your textbook, and I don't remember the page off the top of my head, but it's in the index. And certainly on an exam, you'd have that table given to you. So because of this, it's just like polar and Cartesian coordinates. There's two different ways to look at things. We can look at things in the time domain, f of t, or we can look at things in the s domain, f of s. And so we get different ways of looking at them. But they are equivalent, at least in terms of energy, and they will tell us different things about the system. They're two different representations, two different views. So start looking for the value of the S domain. It'll be really useful. Trust me. When we start talking about transfer functions, it's a great tool. It's also a linear operation, which we've talked about linearity in class. And so, for instance, if f sub 1 of t, Laplace goes to cap f sub 1 of s, and f of 2 goes to cap f2, then what we can do is we can write this just like we did before. We could say, well, a times Laplace of f1 of t plus b Laplace f2 of t. And we know what those are, so it'll end up being a f1 of s plus b f2 of s. And so right away you can see, since this is a linear operation and I have a table that tells me different connections between f of t and cap f of s, then I can split up a complex signal into relatively simple signals, Laplace each one individually, add them all up. It'll be great. It is always a good way to do things. So here's our example. If u of t is u sub 1 plus 4u sub 2, then what is the Laplace transform of u? Well, let's just apply linearity. So we could say that cap u of s is going to be Laplace of u sub 1 of t plus 4 Laplace u sub 2 of t. So it must be just u1 of s plus 4 u2 of s. Nothing tricky there. We can apply linearity. This is why we love linearity. We also know that derivatives in Laplace are really easy to do. So if we've got a derivative, here it is, here's our d by dt of f of t, and we want to take the Laplace transform of that, well, that's just going to work out to be s cap f of s. So if it's a derivative, we're going to multiply the Laplace of the original thing by an s. What if it's a second derivative? Well, we'll do s squared f of s. You know what I forgot? I forgot my initial conditions. Oops. Let's go back to that first one. S f of s minus f of 0. Yeah, you got to have your initial conditions in there. I forgot to put that in, sorry. So s squared f of s minus s f of 0 minus f dot of 0. And a third derivative, s cubed f of s minus s squared f of 0 minus s f dot of 0 minus f double dot of 0. You can keep following this form, but you have to include your initial conditions like I almost forgot. And you can see that in each case, we're just increasing the power of s to match the order of the derivative. First derivative, 1s, second derivative, 2s, and so forth. So we can do derivatives, we can do integrals, we can do the same sort of thing. With an integral, what you're going to see is it's going to be 1 over s f of s. So s is going to represent a derivative operation or an integral operation if it's a reciprocal in the s domain. So anytime you are looking at signals in the Laplace domain, this makes a really interesting point that a derivative and an integral are going to cancel out in a multiplicative sense. And interesting thing, we're going to run into a problem where an integral and a derivative are indistinguishable in S from a system that happens to be represented as an S or a 1 over S, or a signal that happens to be represented as a S or a 1 over S. And so we're going to have to worry about signals versus systems. So let's look at this example over here. If we've got u of s, u of t is 1, f of t is sine of 2t, then u of s must be 1 over s, and f of s, Laplace of that, must be that. What's the Laplace transform of this thing? Well, let's think about that for a little bit. What would that be? Have you got any ideas? What would that be? I think you can see right away that the first term is going to be 2 times u of t. But what's the second term there? What's 3t? Could that be 3 times the integral u of t dt? And you could do the same thing for the 5t squared and the 4 cos 2t. You could write it in terms of integrals. Well, I bet you could, so why don't you work that out? pause the video and work that out, and we'll come back to that in class. In the meantime, I'm going to keep talking. You can work that out while it's paused. Two big theorems that we need are going to be called the initial value theorem and the final value theorem. So if we've got something in Laplace and we want to know, well, what's the value at 0 time? What's the value at infinite time? So what happens to our time domain signal at the beginning of our interesting time period, and what happens at steady state? Well, we can get those from Laplace domain. We don't have to necessarily translate it back to f of t and then substitute it in 0 or infinity. We can do that just in Laplace domain. Remember, I said we don't always have to go back to the time domain solution. And that Laplace domain, if we take a limit as s goes to infinity of s f of s, that's going to tell us what happened at time equals 0. And if we take a limit as s goes to 0 of s f of s, that's going to tell us what's happened at time goes to infinity. So we always know what the initial value and the final value were for a particular f of s. So if we know that, and we've got f of s, and we know that that's the Laplace of f of t, how do we find out the initial slope? Well, the initial slope must be the time derivative of f of t. So slope is going to be f dot of t, which means that the slope is going to go to s f of s, right, minus f of 0. Then certainly we can apply our initial value theorem. So then we can figure out our slope. And I told you we were going to give you a table. Here's our part of our table. This is the sort of thing we're looking at. And so if we know that our signal is comprised of, say, t plus e to the negative at plus sine of omega t, well, we can just Laplace each term individually and add them up. And you're going to see us do this on homeworks and in class. Once we've got f of s, if we want to go back to f of t, what we're going to do is we're going to write it as a rational function of s. So we're going to end up with a rational function and a quotient, and we're going to use partial fraction expansion, which you've seen before. So we're going to break this up into a sum of components, and each component is going to be something off that table. So we're going to take our sum and go back to things on this table, and then clearly we can go back from those to time using our inverse Laplace transform. So you'll see it a couple times, it'll make more sense, but the point is that we always have to break it up into chunks that we know and then convert each one individually. Just the same way as we converted time to Laplace, we put it into terms that we knew, looked them up on the table, and there we go. So here's an example. If we've got distinct poles, which is to say that we've got no repeated roots of the denominator, then we'll say that f of s is going to be b of s over a of s, and so it's going to be some product of s plus z's, which zeros, over s plus p's, poles. Then we will say, by partial fraction expansion, that must be a1 over s plus p1 plus a2 over s plus p2, and so forth up to an over s plus pn. And certainly, we could cross multiply and figure out what a1 through an are going to be, or we could apply the residue formula, which conveniently I was just writing that down there. So we could cross multiply and solve, or we can use the method of residues, and there's other tricks to it. But once we've got each one of these terms then, so this one, and then this one, and this one, each one of those should be something off of our table that we can easily inverse Laplace back to time domain. If we've got multiple poles, like this one's cubed, so it's a repeated root of the denominator, well, then we have to do things a little differently. We have to say b over s plus p1 and b over s plus p1 quantity squared, and b over s plus p1 quantity cubed. And so we get three different things that we're going to have to take back to time domain. And you'll see examples of these on the homework. So that's how we're going to go back and forth time domain to Laplace and back. And then we will use things a lot in Laplace domain. Laplace domain gives us a lot of insight in the behavior of the system. Looks like that's all the slides I've got on our theory section. There's going to be a video posted as well for examples, just so we can practice this stuff. And we're certainly going to practice this with respect to dynamic systems that we are looking at, mechanical systems, electrical systems, fluid systems, any one of them. It all goes into Laplace the same way. And remember that you can have the same ODE describe different systems, which means you can have the same Laplace format, the Laplace representation of a system that describes many different types of systems. And so in Laplace, there's no way to say, is it mechanical, is it electrical, is it fluid? It's just a representation of the system, and the system representations can be equivalent, just like you saw with the electromagnet and the paint sprayer. So I'm going to leave it there, and we will have a video of examples next.